learn how to develop and deploy sampling-based motion planning algorithms on an Arduino or an ESP32 microcontroller. We'll be using an ESP32 for this exercise, where you will develop a GUI using Qt, along with use QSerialPort and QCustomPlot so that data can be sent back from the ESP32 to your computer and you can view it in real time. And you will need to have the following to accomplish this task. Let's begin. Okay, let's begin with our motion planning review. A quick review of the RRT algorithm. We have a start location, a goal location in a map. We have to define a tree which will connect the points. For now, I'm skipping 2 steps. I will not have any obstacles just for now, and also I will not show you the path from the goal to the start because that will be an exercise for you. Okay, let's start. So we have the first step is to sample a point, sample X and Y. Then you have to steer to a point. You have to find the nearest node. These two have to be done sequentially. And then you add the child. So let's begin with sampling. Let's say I sample over here. Let's use a different color for this. I sample over here. I have to steer to the point, and the amount I steer is a fixed value. I'll call it the radius. Radius, just like that. And that is a constant value. And so this radius, let's assume that it is about this distance. So I'll just draw it over here. When that's done, the nearest node, we just have one node, so it'll be the start node, nothing else. I then add my child, so I just add a child like this, and I also have to connect its parent back. So this node's parent is this one here. Let's repeat this. Let's use one more different color, green. Let's say I sample over here. The nearest node is the start node here. Okay, let's say it's over there. I steer to my point, so the same distance I steer, so this will actually end up being over there. And then I add my child once more, and then connect its parent back. Let's say I do this multiple times, so let's say I find my nearest node, that is my start node. And then, or actually it's this one here. And then I steer to the point, so I steer to it, so it'll be about this distance. This will end up being there. I add my child and I add my parent. Let's do one more iteration. I think you're seeing the pattern by now. Let's say I sample over here. Nearest node is this one. I steer a fixed distance away from it. So to here, I add my child and then I add the parent. If I keep on doing this, I will eventually reach somewhere near the goal node, at which case I will append the goal to my tree and then I will just sample back. So let's just draw a simple tree. Like, imagine we end up with something like this. Let's draw their children. Let's assume that there are more sample points, but I'm not showing them for now. When I sample near the node, I will append the node and then traverse back. Okay, how do I traverse back? It's very easy. Each node has a parent pointer, so all you do is you go from the goal dot parent back to the start, and you will end up with this path. Each tree node will have a bunch of attributes. The first one is children, pointer, a parent pointer, and then a next pointer. Children.next will take it to its next child. So these two nodes here, 1 and 2, are both children of node A. The parent of node 2 is also node A, and I will implement it like this. I will use a linked list because on embedded systems, you have limited memory, which may not be contiguous. I will explain that very soon. So just bear with me here. Imagine this node 4 is the child of 1, so I will add a node like this and a parent pointer back. The next represents my linked list here. So children, and then we have parent, and then we have next. These all point to node objects. So let's look at how we will actually implement this tree in the embedded platform. Now keep in mind that we are using an embedded platform, which means that we cannot use any sort of STL library in C++. Everything has to be raw pointers. And this will actually teach you a lot about how pointers actually work. So you will appreciate how things are stored in memory, and this is a good exercise to learn about the details of pointers and how you can access them, and also how you can build effective programs without copying of objects or using excessive resources. So let's start. So we have the root node. So when we define a tree, we have normally a node and then we have connections, right? Like we have, that's your first child, your second child, your child over there, and these are all node objects. So let's draw a quick example over here. So let's build up this here in an embedded platform. So let's first define the root node. So that's my root here. And let's say we want to add 2 children. First, let me tell you how I did it, and then I'll explain after. So let's first add the first child. That's my first child over here. And I want to add 2 more children. Now, no STL, right? Like, remember that. But I want to connect more children. So what I can do is have a next pointer. And this can be used to add my second child, just like that. And if I want to add another child to this root node, just add another next pointer and then add a child over there. Let's say if I want to add more children to this node here, if I want to add 2 more to this one, I can once again draw a children pointer and then add it. And if I want to add another child to this node here, I have to add a next pointer and then add my child over there. I will also need parent pointers, so I can also add a parent pointers to each of the node here. So this one, this parent is also this one here, and this parent is also this one over there. The same with this one here. This child is parent is this one, and this child parent is this one. And if I label them, so next I have children, and then I have parent here. So if you look at this, you can define a generic node, which is any node with these 3 pointers. So the first one will be the children, the next, and the parent. The root node will have no parent, so its parent will be set to null, and the next pointer will also be set to null. So for the root node, which is this one here, these 2 don't exist. You will only have children and then go from there. So why I did this, right? The first reason is I can't use vectors or arrays even, because think about how C++ works with arrays. Every time you resize an array, you copy it and you paste it into a new memory location. Now, do we want to do this in an embedded platform? We don't, because it is not good to always allocate memory every time. It's best to use fixed memory locations and just work with that. So which is why I used a linked list instead of an array. So this children array, it's actually a linked list, because I don't need to store these nodes in contiguous memory. They can be stored anywhere. As long as I have the pointer, I can always access the next connecting element to it. If I show you a diagram over here, on the right side, we can see that the tree node is defined this way. We have a linked list of children. We have a parent pointer, and we also have the next pointer. So the next pointer lets you iterate across, and this tree on the right is the same as this tree here on the left. So these 2 are the same thing. It just defined differently. I don't use vectors and arrays because of, first of all, I don't want to copy and paste into new memory each time. It's best to do everything in place. So that's why a linked list is the best application over here. Think about an embedded platform. Imagine a board or some type of microcontroller. You only have limited memory to work with. And a lot of the times arrays can be very large, so you don't want to allocate memory each time, because imagine if it copies and pastes into a new memory space, you might have the case where you don't have that much of space available even, so it'll not work and you will have undefined behavior. Now let me explain how I add arrays and nodes into my tree. So let's define a root node and let's define this node pointer array. So let me draw an array here. 7 nodes we can store, and let's start building them out. The first thing I define in my tree is my root. So that's my root node here, and I will also draw it over there. I want to add 2 children to my root node. So the first child will be, I add my first child, then I will basically have a second child. Its next pointer will point to that one. And then I will also add this pointer into my array here. Say if I want to add a child to my first root child, so to this blue node here, I can draw that once more. And I can also add this to my array here. So think about how the pointers are being allocated to this array. When we first make the root, we have one node here. The number of nodes is equal to 1, so I'll assign it to the first element of the array. This is actually index 0, but index 0, index 1, like no big deal. It's just the first element of my array here. The second child I add is my first child to my root, so this will go into here. Number of nodes becomes 2. Then I add my third node. I allocate the third point in my array. So every time I add a node, I increase my number of nodes by 1, which is an integer, and then I just allocate that element in my array. So if I have, let's say, 5 nodes here, so if I have like something like this, if I add one more node, this will go over here, which is node 5. And then if I have a child over here, like node 6, for example, so node 6, I will keep on adding nodes like that. So every new node I add increments this integer value number of nodes by 1 and also allocates the point in my array. So let's talk about why I have this array and what's the significance of it. When we normally search a tree, we do 2 things, right? We do breadth first search or depth first search, BFS or DFS. We need to use a second data structure, a queue or a stack. In BFS, we use a queue, and in DFS, we use a stack. But why do that? Like, why use extra space if we can just have one array of a fixed size array, which will just store the pointers? Remember, you're not storing the copy of the object, you're just storing its pointer. So this object will be stored in some memory address. I'll call it like X, Y, Z. This node 2 will be stored in some memory address A, B, and C. A, B, C here. So this X, Y, Z will be stored over here. I'm not storing the actual node object there. I'm just storing its memory address, its pointer. And this will be A, B, and C. This way we can use the least amount of memory possible. Now, if you think about this in more detail, you can see why I don't use a queue or a stack. How is a queue implemented? Think about that. It's also an array or a vector. So if I use a queue, if I use, let's say, a linked list for my queue, I will actually modify this tree, which I don't want to do. Because in my queue, if I move the pointer there, let's say if I have a queue of pointers, right? Let's say if I have a queue of pointers like this. If I'm doing, let's say, breadth first search, I'm doing level traversal. So it'll be like 1, 2, 3, 5, 4, and 6. If I store my root node here, okay, that's fine. And if I store this one, node 2, if I pop this one, if I say 2.next and store it in my queue here, it'll actually affect this one. It could change this one here. Because if I store, let's say, 3, and then if I store 4 and 6, this 4 and 6 will go over here, but then this will also change to 4 and 6 here. You will add another next element, in which I don't want to do that. Because remember, my queue will not be an array, it'll also be a linked list, so it'll also have its own next pointer. So the objective is to not modify this tree at all and to just use pointers to traverse it, and that's why I'm using this array here. Every time I add a node, I can just append to this array, and then if I want to find the nearest node, so let's say if I sample a node over here, the nearest node is node 2. I can basically just search my array and then get my XY location and then find the nearest node to be 2 here and then assign the children like that. So when you see the implementation, you will get it because I will show it in more details there. But basically the idea is that I have a tree. I have an array which stores the pointers to all the elements in my tree. And every time I traverse the tree, all I have to do is search the array. I don't need to use a queue or a stack or do BFS or DFS. And this will be very useful in pointers because if we use a fixed size array, then in my memory, in my ESP32 or my any other microcontroller, I just have one contiguous memory to store my array, and it'll be a fixed size, so it will not change each iteration. In this picture, you can see a more clear diagram of my tree, which I explained before. Every time I add a tree, I add its memory address to the node pointer array here. So in this case, we have B, C, D, which are children of A, and then E and F are children of B. So if I want to find, let's say D, it'll be A.children.next.next. If I want to find node F, it'll be A.children.children.next. If I want to backtrack from F to B to A, it'll be F.parent.parent. So you see how the pointers will take you to the next location and you will be able to kind of connect each node to its parent and to its children like that. I can use this array to search the tree because the pointers will be stored directly in here. And as I explained before, I don't use level order traversal, a queue or anything like that because a queue will have its own linked list. And in that case, you will have issues because if you modify the queue in a different order, it'll actually modify this tree as well because I'm working with the same pointer locations and not creating copies of any objects. Another question I ask for your thinking is why not recursion? In data structures and algorithms, we can also use recursion to search a tree. We can do a depth first search, and in this case, all I would have to do is make a function that takes in the root and then it says search root.children and then root.next. So it'll keep recursively calling the entire tree. The reason is because think about the recursion stack depth. In operating systems or in programming languages, you have something called a stack depth. And in embedded platforms especially, you have limited stack depth. If the recursion stack gets too big, you will have stack overflow, and that's terrible for your program. You will crash and have very undefined behavior. So I try and do it iteratively, and I avoid recursion in embedded systems. Now, if your tree is not very big, it is okay to use recursion, but at the same time, if you look at like real world applications, this tree will become big. If you're searching a large space in a map, then the tree you will have many points, and if you recursively keep on doing it, you will just create a big stack, and that's not the best idea here. So that's why I iteratively search my array. So all I have to do is use a for loop and then search index 0, index 1, 2, and go from there. This array, just to recap, is a fixed size array. So I will not modify its memory space. It'll be one fixed memory space of some size, and I will keep appending elements to it. When this array becomes full, the tree will become full. So that is why I will assign a large space to my array so I can keep appending elements without having to copy it. Let's look at the GUI first before going on to the embedded code. So in my GUI, I'm using Qt. I've made many videos on Qt before on how to use a GUI for your embedded platform on Arduino. So when I make a new project, I just add two things. The first thing is serialPort because I'm using QSerialPort for my project, and also print support because I'm using QCustomPlot. I'll link two videos in the description below on how QCustomPlot works and how you can use it to plot your data. So I add two files, QCustomPlot.cpp and .h, and this you can download from the official repo. They're added into my headers and my sources respectively. So let's look at the UI first. I have a received X, a received Y. So that's my point which I receive and my number of nodes, which I can always update. I also have a widget here, which I have promoted to QCustomPlot. So if I look at this right hand side here, I have this custom plot which I will use to plot a graph. This graph will contain all my tree nodes, their XY locations. Since each node is an XY point, I can just plot the values and go from there. And to understand how I did this, I recommend you watch the video below on how QCustomPlot works, and you will easily be able to create this yourself. I just don't want to repeat what that creator has done because he has done a very good job explaining it. But moving on to the source code here, we have dialog.h. So let's go over here. Before that, QCustomPlot.h, don't change anything here because that's just copied and pasted from QCustomPlot website. Okay, let's look at all the variables I define. I also have two methods here. The first one is update value, which will update this text over here with each node that I receive. Let's look at all these points here. Now, the first one I have is X receiving new. So that's the new node in my tree which I receive. Same with the Y. This one is XY of my nearest node because the nearest node is my parent. And I need to get 2 points. I need to node and its parent too, because if I just receive the node without its parent, then when I plot it, like where do I connect it to, right? It has to be connected somewhere. So that's why I need the parent node as well. I also have a QString list, a buffer split. So that's my serialized data which I receive. I have a QVector branch X and branch Y. So that's a node line. So a branch, think about a branch, it's between two nodes. And I need to have 2 for X and Y here. I have a QSerialPort object which I define ESP32 for my case. I have a UI. I also have this vendor and product ID. Now in my video on how to use a GUI with Qt on Arduino, I showed you exactly how to get this vendor and product ID. So you can refer to that. In my case, it is 4292 and 60,000 based on my ESP32 which I have. I also have a bunch of variables here for the port name, the Boolean. If the ESP32 is available, I can receive the data from it. I have my Q-byte array, which is my serial data, because that's what I receive from QSerialPort. And then I have a QString serial buffer. These are the variables which you will need to access your tree and to plot it on the screen. And let's look at now how they are implemented. In my dialog constructor, I create a new QSerialPort. Initially, it is not available, and I have an empty serial buffer and port name. I then find which port my ESP32 is on, and I assign the names respectively. If they match the vendor and product ID, I just assign my port name and then I say port available and go from there. Now this is explained in that video, in my GUI video, so I won't go over it again here. If my port is available, I can start to receive data and configure it. So since I'm only reading data and not writing, I just make it read only. My serial rate is 9600, so I set it to that over here. And then I create a state signal and slot. The update values, the slot will be called every time I send data back. And then I can draw my graph and configure it. So in this case, I make a new graph. I set my x-axis limits, y-axis limits. I make it interactable so I can zoom in and drag across. I set my label of x and y. I then resize my vector to make it size 2 because it'll be node A and node B. And then I set my root node. So in this case, I use 10, 10. So x and y are both 10. That's my root node. And then I just set my data like this. And then just plot my root node first before I even receive anything. And then I set my styling. I just use black and red in my case here. This can be up to you. You can just look at the documentation of QSerialPort and QCustomPlot and then go from there. Now this is the update value. This is the hard work here, and this is where everything goes. So what I'm doing here is I'm simply saying I'm parsing my data. So my ESP32 will print data in a specific way to the serial monitor, and it'll be received by QSerialPort here. And if you look at this picture, which I will show you right now, you will easily understand how this works. If you look at the elements in my serial buffer, it is split by the comma value. It's called delimiter. So I split that, and then I just take the specific elements that I need, which is elements 1, 2, 4, 6, and 7. And then I parse them, I convert them to a float, and then I create a new branch. Then just add a graph, because each branch I plot is a new graph. It's not the same graph. So you have to do it this way, and then set data, and then just do a replot. When you are done all this, you will reset the serial buffer. And that's it. It'll keep on going in a loop. So this is how you will receive your information. It's called serialization of data. This is done in every application out there. When you send data over a network or over like two devices, you have to serialize it because it has to be readable by the other side. And especially with trees, you have to send minimum 2 points, the node and its parent, because the graph has to know where it is connected to. And that's how you can do it like this. The syntax, don't worry about that's just Qt specific, and you can easily find this on the Qt documentation. So that's it for the GUI, and this will work with my tree. And now I will show you the embedded code, and then lastly how they all interact. UML diagram for my planner, my motion planner, and my tree node class. So I have a main that creates an instance of this planner, which will create my tree and then send it to my UI over QSerialPort. The ESP32 will be loading all the node objects and creating the tree on the platform. So let's look at the tree node class here. I have a XY, which is a float of size 2. I have my parent, next, and children pointers with my constructor and my destructor. So when I create my node, I must always pass in an X and Y location. It should not be undefined. And then I can define my XY node from there. In my planner, I have a float of XY. I have my node pointer array, which is I use for now size 100. This can be any size you want based on your resources available. It's a size array of pointers of 100. I have my tree node root because the tree starts at the root. I have my sample X, sample Y, which is a point which I can just sample and append to my tree. Number of nodes, my nearest node, and then a radius, which is the tree distance, which I explained before. I also have the planner itself, which will create the node. So I must pass in the constructor there, which is my root here. So this X and Y will be the root node. I have a method addChild, which will just add a node and then take an XY point, create a node, and then add it to this node over here. So this child will create a new node and add it to this one. So if I call addChild A, and let's say X and Y is equal to 10 and 15, it'll make a node B and then add it to A here. So B will be 10 and 15. Steer to point, you saw how that works before. Sample X and Y, I'm just sampling a point. Process node, this will take the pointer and then add it to this array here. So it'll update this node pointer array. I have print information and then find nearest node. And that's self-explanatory how they work. So now let's look at the ESP32 code. So now finally we are in the ESP32 code. I'm using Platform IO, which is an IDE for embedded development. I do recommend you use it. You can also use the Arduino IDE. So I have my tree node class header file. I include my arduino.h because I need it for the sampling. My XY location here, pointers to parent, children, next, and then my constructor and destructor. In my planner class, I have the same stuff which I talked about before. My root node, number of nodes, node pointer array, sample X and Y, nearest node, because I need to add the child to it. My constant radius, constructor, destructor, addChild method, steer to point. And then I have a bunch of inline methods. So inline means that In C++, you have an inline function which is faster than a regular function because you skip the caller to it, and I define it within the header file itself. So sample up x point. In this case, I have 100 in x and then 50 in y. This can be any number for now. I'm just testing these two here. I also have process node, which will basically, it just assigns the node pointer to the array at the specified index, number of nodes, and then just adds 1 to number of nodes here. And then I have print information. So this gets sent to QSerialPort to my UI. So if you look at this, it'll be new sample x, comma sample y, comma number of nodes, comma nearest, and then I can print my nearest node if it is there, because it may not be there always, right? So you see how this will print out a statement which is comma separated, and then in my QSerialPort you saw how I could take that statement and then parse it and then obtain my values from there. So this is a basic example of serialization, and you will see this over and over again in the workplace, in your projects, and in typical applications. Lastly, I have my find nearest node. Let's look at the definitions now. So in my constructor, I just define my tree node here. I just make a new node, and then I just say, okay, xy0 equals x, and then xy1 is equal to y. Initially, when I define my node, you have to set this to null pointers, because otherwise, I've noticed in C++ on a PC or a Mac, you don't get any bad behavior, but on an embedded platform, if you don't define a pointer to be a null pointer, I did get a crash. So make sure that these are null set like this. And I can delete my node recursively here. In the planner, let's look at that. I create a new node when I pass in my root with the start x and y location. The nearest is set to null because this is again a pointer. So this has to be a null. Any pointers you define will have to be a null here. And then I just have my add child method. So let's look at this one. This is very interesting. This will add a child by creating a new node with this given x and y location and add it to this node here. So you see how what I did here? If the children is set to null, I assign it over there, but if it is not, then I have to actually get to my children and then check the next pointer. So while that is not equal to null, I just iterate over to the next pointer and then add it if it is a null pointer. So this should make sense according to my diagrams before and how I explained to you how I add my child to my parent node. Lastly, I have to assign this node's parent. So this parent will be this node over here. Then there's one more step. I have to actually update my array, which I talked about, that node pointer array, fixed size array. So I just do that by calling process node here. Then I steer to my point, and then I can find my nearest node. So here, what I do is, all I have to do is search the number of nodes I have. So if I have 10 different nodes, I have to search all of them. I just use a basic minimum search algorithm. I get the pointer from my node pointer array, and then just get its XY location. So this is X and that's Y here. I just looked at the Euclidean distance between the two. And if it is lower than the distance maximum, which is some initialized to some large value, I get my nearest node and then it'll just update this nearest node over here. So that is pretty much the class definitions. And now I will show you in the ESP32 how I use FreeRTOS to implement this. Okay, first thing I do is I include my files that I need. I have two methods to create the tree and to print information. So this will be one task. This will be another task. I use a global variable for my planner. I just create a random tree. I pass in my root at 10 and 10, which is what you had seen in that QCustomPlot. I have my setup here. The serial rate is 9600, which is the same as the QSerialPort. It has to be the same, otherwise you will not see the text properly. I create one task to create my tree on core 0, and then another task to create my printing on core 1. So the ESP32 has two cores and you can leverage this. So you will get some concurrency there. If you have a single core or an Arduino, then the task will still run, but they will not be concurrent. You will have a task scheduler going on there. The loop is empty. because this will create the task which will keep on iterating. Okay, so this is very simple. All I do is I call a bunch of methods to create my tree. First thing I do is sample a point, find the nearest node, steer to point, and then add the child. So you should understand how this works. Very simple. And the next task is to print the information. So that's pretty much it for the ESP32, and now let's see how it works with the GUI in Qt. So to run your code here, just connect your ESP32 and then press build. Time this correctly. And then when it is like 100% done, press upload. And just when it's about to upload, make sure you open your Qt application because it should load your data into it. It has to be timed here. So there we go. You can see now on the UI that the number of nodes are being received and it's sampling the points. I did miss one node by accident because I think I pressed the upload button too late. Now you can actually take this further and have logic to actually time the uploading and stuff, but that would be like too complex for this video. But that's something you definitely can do. Or one thing you can do is add a time delay for maybe like 5-6 seconds and then reduce it after that. So you can see if I go in the monitor on Qt, you can see it in the debug there, and it's also printing the nodes on the graph. You can zoom in and magnify the graph if you want to. So it looks quite nice. And now since this is RRT, it's not the optimal RRT star. The tree looks scattered all over the place. If I close and open the UI again, you can see that the graph is now gone because the old UI shut down. But there are the number of nodes still updating because the ESP32 is still running in the background, If I open the monitor here, you can see the same thing. The ESP32 is always on. It's always doing the calculations, and it doesn't matter if you have your serial monitor on or off. It'll just keep on doing it in the background. And it's sending the data back and forth over here. You can see that the number of nodes is always the most new number at 46 now, and it'll keep on updating it. So there are ways you can make this app better. One thing you can do is have a database which stores all the node objects, and then if you open the graph again, it should load that along with the new points. There's many things you can do. You can synchronize the way you start up your sampling algorithm and make sure that you also get the first node in your graph, because I think I missed it here. But overall, you get the idea of how to actually pass your data back and forth. So that's it for the video, and thank you for watching.